Good afternoon, ladies and gentlemen, and welcome to this webinar on Masterseries flat slab design. Very welcome to everyone in attendance here today. With me, my name first of all is Martin O'Gara. I'm a software engineering developer with Masterseries, and answering your questions here today is my colleague Tommy White. So any questions that you do have during the process of this presentation, feel free to type them into the questions box on your GoToMeeting or GoToWebinar panel, and Tommy will be answering those as you go. We are here today to look at the two different methods of flat slab design that we can offer you. First of all, and the one that we have had historically right from the beginning of our the development of the Masterseries programs, is our MasterFrame flat slab construction. Now this is not a finite element based method, but it is a method based on the column strip design methodology outlined in the BS 8110 section 3.7. So I think perhaps the majority of us here today are UK engineers and would be familiar with the British standard and this design methodology. It's a methodology obviously based on frame analysis and interpreting those frame analysis moments and shears to distribute those and to break those down into a method for providing reinforcement in slabs. And it does have its pluses and minuses. Perhaps one of the things that most people like about it, it is quite an engineering friendly approach, quite easy to understand and to follow. It also produces quite a rational presentation of reinforcement because it automatically talks about column strips and middle strips, and even the column strip is split up into the middle half and outer quarters, so automatically you get zoned reinforcement and nicely presented reinforcement in different categories and zones. Perhaps on the other side, the slight disadvantage of this method, or perhaps increasingly more so the disadvantage of this method, is its geometrical restriction, in that it does favour itself more to regular column layouts or moderately irregular column layouts. We have been able to stretch that restriction, I suppose, to its limits, and you can possibly get away with a bit more than you might appreciate. The other method we're going to talk about, the MasterFrame finite element method, whereby it kind of turns its advantage and disadvantages on its head with regard to its previous method, in that there are no geometrical restrictions as such in terms of the shapes of the slabs or the layouts of the columns or anything like that. It perhaps is a more accurate method of analysis than the 8110 column strip approach. Perhaps one of its disadvantages is that it is less design orientated, and I mean that by saying that there's perhaps more interpretation and work to do to interpret the finite element analytical results to produce sensible design results. And we'll have a look at that as we go. So let's just get rid of this little slideshow and let's not waste any more time and really just begin looking at these two different methods. Okay, I'm going to start looking at the MasterFrame flat slab construction method first of all, so the 8110 column strip design approach. It might be useful for us to have a look at some of the frames that people have put together using this method, and you can see here quite a simple slab, pretty regular column layout as we can see. It looks like we've got some downstand beams around the outside of that slab, which is possible using this technique. We'll just have a look at one or two other files as well before we perhaps go through a quick process of generating one of these frames for ourselves. So again, pretty regular column layout with perhaps a bit of irregularity in the shapes of some of the perimeters. There's nothing stopping us going into a multi-storey frame type arrangement here, and putting this on plan helps, I suppose, to clarify the sort of column arrangement that we're looking at. And you'll see with lots of these things that we're talking about here, there are some golden rules with regard to the geometrical restrictions, and one of which is it is certainly preferential to form four-sided panel shapes. Every single horizontal member really needs to be a column strip which goes between the head of one column to the head of another column. So for example, in this type of scenario, we've had to put a column strip from this column across here, creating a triangular panel arrangement, which we are happy to deal with, but naturally a column strip going from here to the middle of another column strip isn't really in line with the concept of the actual method. So just flicking through one or two little other files. I mean, naturally any of these we can put on 3 dimensions and see the slab being drawn as such. Okay, to that message, and just one or two more unusual or less regular shapes than the standard rectilinear arrangement. I'm going to go through a little process of generating a frame just like this, quite simple and straightforward, just to really go through the processes of putting it together and interpreting the results. So let's create a new frame. I'm going to call it FS2, and the first thing we're presented with are some flat slab basic data. If we are going to go multi-story, what are the different slab thicknesses in each of the levels? I'm going to just have one story that's 250 mm thick. Flare heads and drops, I actually don't want any of those, but I'll sort those out in a little while in terms of the column properties. I can access all of this data at a later stage, but it's helpful for me to simply specify what I want at this stage. Just reduce my dead and live loads a little bit. We have some slab projections and offsetting dimensions from the distance to the edge of the slab to the face of the column. These types of things which can influence punching shear perimeters and such. So all of that information can be specified there. We can also specify drop edge beams and the dimensions of them, both downstand and upstand edge beams. So let's just simply go ahead with this. And I'm presented first of all with a simple preprocessor of putting together a frame. I'm just going to go for, sorry, that actually was 5 spans that I wanted, and reducing myself down to 1 story. Default span of 6 meters, height of 3.5. I'll leave the flares and drops in just for a second, and then I'll take those out in a little moment or two. We have this special flat slab menu in the flat slab, MasterFrame flat slab construction. Now users of MasterFrame will recognize this environment. Is it actually quite similar? It is very much a sister program of MasterFrame. All the same geometrical editing tools are available to you, as well as loading tools. The full area loading techniques of the Masterseries 3D Model Manager are available to you here as well, for both area loads, line loads and patch loads, regardless of whether you're licensed for the 3D Model Manager or not. For your general frames, you do get all those facilities here. But the flat slab menu lays a little, if you like, crib sheet out for us of how we might go through the generation of a flat slab. What I'd like to do first of all is simply use the flat slab duplicate technique to come and say, well, I'd like to move this frame or duplicate more of these frames in the Z direction, and let's create another 6 of them and proceed to produce something like that. So falling back on more of our basic MasterFrame geometry editing tools, let's have a look now and say that we want to delete some nodes to change the shape of the slab. So we'll just take that all the way from there, say down to these locations, deleting all of those nodes, and again those 2 sets of nodes there to produce that. And finally, just to create the shape that I want, back to delete a member here to create a little recess in this slab of that sort of nature. And back to geometry, I'll just shift a column around to create a little bit of irregularity, and I'll just take that down by -1 meter in the Z direction. I'm working with this structure on plan and windowing nodes because it obviously then picks up both nodes together, and it creates the right type of shift that I'm after. I could go a little bit further in terms of the geometry, but for most of us who use MasterFrame, the same principles and techniques of how you edit the geometry is applicable. The only thing you need to be very strict about is the fact that, as I said before, all of these horizontal members are column strips which really must go from the head of one column to the head of another column. Back to our flat slab menu, I can visit my area loading defaults and change the values of area loading that were set up in the basic data area. I can also come to my gravity area loading and go into either my member area loading groups, whereby I can see from here already that the program has already set up all of these members in lots of member area loading groups for me, and everything is all automatically loaded in terms of the gravity area loading. But what is more useful is this edit panel if you wanted to make some changes, which we can access here as well. And in the edit panel, one can specify or click on a panel to do lots of things, such as changes the depth of the slab as to override the overall global depth and the dead and live loads. Perhaps what I will do here is just create a little opening in this, whereby, and that's really done by coming in and specifying the projection from the edge of the panel to the start of the opening. So if I were to produce something like this, to create that style of opening, I'll just put that on plan so you can see it a little bit better. Maybe take that back a little bit, 2.5 that way and maybe 1.5 the other way. And that has the effect of really reducing the width of column strips and concentrating reinforcement over other areas. And it also will affect the punching shear perimeters and such as well of related columns where that would interfere with that. One of the restrictions we do have here with this is that an opening can't really intersect a column strip, because that completely interrupts the integrity of the column strip, and it's no longer really a column strip. So you would have to think about rearranging your column strip members to be able to create an opening in this sort of region, and that's actually one of the things that's more difficult to model using this geometrically restricted approach, basically. We can, of course, come in and do some gravity area of line and patch loading, similar to the 3D Model Manager in every way, but I'm not going to do that now, just to save myself some time. For the columns, I can visit the properties of those columns and edit them in the same way I would for a standard column, but this has a special type of column for flat slabs where it has flares and drops. But I am just going to go into global mode, take all of these columns, and I'm just going to remove the flares and drops, so I just end up with a straightforward square column, and as I can see that's the case now, and looking at it in 3D I can see the overall shape that's been presented for me. And one of the things that we do ask you to keep an eye on in the flat slab is the program's interpretation of beam runs and patterns on those beam runs. So for example, if I were to go to say, check the beam runs and load pattern numbers, let's zoom in a little bit here and actually exit from the properties area. And really, again, coming back to the actual 8110 method, we're going to have beam column or runs going in the east-west directions, and also then a separate set of runs going in the north-south directions. Those runs also will be alternating in terms of the load pattern, so we've got red, blue, and the same thing in the other direction. Basically every run making sure that you have alternating loads and the same thing going in the other direction, this is a run. Now the reason why we check those is because perhaps in more complex geometries where we're really pushing this method, you might need to intervene and say, well actually no, all of these members I want to be part of the same run, and that's something that you can step in and override, and you do that through this change column strips area. Now that's not something I'm going to go into today, because this reasonably regular layout has no problems with that regard, but one can go in and reassign certain members into more appropriate groups, getting into the more advanced end of how this is controlled. So what I want to do really now is have a look at the loading on this structure. And I can see from the loading that I have different cases automatically produced for all spans loaded in an east-west direction. And then I have the alternating nature of those. And quite simply then all the spans get loaded fully in a one-way spanning direction, independently north, south, east, west, all spans loaded in the east-west direction, and the alternating nature of those, followed by a few service cases as well, and that completes my setup of loading cases. So that's what we're analysing, and let's do that. And we'll have a quick look at the output, just to satisfy ourselves that everything is as it should be, and also help us to understand really the nature of result and bending moment that the actual design end will work with and interpret. So we're getting bending moments again from the three cases in one direction with alternating patterns, and the three cases in the other direction with two alternating patterns as well. So for example, if we would go back to loading case 1, it might be interesting just to have a quick look and say show the values, and we see a value here of 190 in the sagging. I'll just select that for major axis only, and 325, 314 around that column head in that east-west direction. It might be interesting just to take a mental note of those figures and see how they're worked with, interpreted then when we get through to the actual design phase. Because of these, obviously, moments are column strip moments, they're not the actual moments in the slab. The 8110 gives us the technique for how to interpret those moments so that we can produce slab type reinforcement, and those are exactly the rules that we will apply to those moments to achieve your actual design. Coming in here, yes, C30 concrete, main steel and shear reinforcement of those sorts of natures. What it's also asking me in this area is also, what is the basic common area of reinforcement that you would like to provide in the 4 different main zones of reinforcement in this slab, i.e. reinforcement going in an east-west direction on the top, the north-south on the top, and then the 2 principal directions on the bottom. And I'm quite happy to let everything go with 10s at 200s at this stage with these covers, which you can change or invert if you want to have your reinforcement going in different ways. Thinking about it, what I have here, I've got a larger span in the east-west direction, so it makes sense for me to have that reinforcement with lesser cover, obviously, so that it has more effect. So I'm happy enough with the way in which the cover has been organised and arranged for the slab. I also have the minimum bar size that the program is going to use for any additional reinforcement, and the spacings then it will work with for that additional reinforcement over and above the basic, which will be always there. So let's have a look at what the design actually gives us. In design mode, we have all these different modes down here of how you can investigate the quantities of reinforcement. So if I were to look at this member, the program is saying, well, with this member, I've got east-west column strip along member 5, so that's and it's in the bottom, so it's the bottom reinforcement along this direction. In fact, it can be helpful to use this little tool to say, show me all the reinforcement associated with this. So I've got 10s at 200s along the bottom, which is just really all the basic reinforcement at the moment. I then have north-south middle strip steel at right angles to member 5 on the top. So this is this reinforcement on the top at right angles. And then also middle strip steel, which is this part, associated with member 5 also. So this, for example, tells me that the east-west column strip steel goes from 1.25 meters south to 1.25 meters north of this strip. So starting off somewhere down here and finishing off somewhere up here is this quantity of reinforcement, but it's not sufficient. I've only just got the basic. So one of the things that I might like to do now is simply do an automatic design. I can either do an automatic design, or I can come along here and say, well, actually I would like to have a further 10s at or 8s at 300, which is just enough to give me 560 provided reinforcement against this amount of required reinforcement. But I can simply do an auto design all, or auto design for this area, and it shows me what additional I require for all of these different parts. So now I'm showing all reinforcement. It actually makes it a little bit better to show just the additional reinforcement, because the basic's always going to be there. So this is the additional amount of reinforcement. Now that auto design works for this just individual part that I'm looking at. If I look at a column, I can look at the reinforcement above the column head, but I'm simply just going to say auto design all at this moment in time. I'll now switch away from this individual member, the localized reinforcement around a member, but now looking at reinforcement in an overall sort of fashion. So this is the additional reinforcement, and I'm saying here this is all my east-west bottom strip steel. This is the additional, so I've still got my 10s at 200s, but everywhere it looks like for all the bottom strip steel I'm needing additional 8s at 300. If I look at the other direction, not everywhere, but in certainly lots of locations again, the bottom strip steel in the north-south direction, I'm looking for additional 8s at 300. Looking at the top, it starts to get a lot more cluttered, as steel does on the top of a slab. Obviously the 8110 tells us to provide reinforcement in a column strip, but also it divides the column strip into its middle half and 2 outer quarters, which is precisely what we're doing here. So we're saying we need 8mm bars at 75mm centers in the middle half, and then the outer 2 quarters an additional 8 at 300s. Now that's obviously quite a complicated arrangement of reinforcement, but so what I would really like to do at this stage is to go back to the basic amount of reinforcement and consider how I can change that or increase it, perhaps so that I have a more common value of reinforcement everywhere. And let me take that up to, because the east-west direction is a larger span, I'll perhaps take that up to 16s at 150, and I'll take that up to 12s at 150 in the north-south. In the east-west I'll say also 12s at 150 there. Perhaps in the north-south I might get away with just simply 10s at 150, modifying my basic amount of reinforcement globally for everywhere. And now let's simply do an auto design all again, and I can see certainly no additional amount of reinforcement is now required for the east-west bottom strip steel. I'm perhaps providing for the 12s at 150 quite a bit more in some cases than, well, certainly for this strip, but basically I'm not requiring any additional reinforcement either in the north-south or the east, or north-south or east-west. For the top reinforcement, it looks like, I'll just zoom out a little bit here, again no additional reinforcement in that direction. For the other direction I'm getting some localized reinforcement in the middle halves of the column strips. You're getting 8s at 200s, and again I can control that, whether, you know, you might say, well, I actually wouldn't want to use an 8mm bar. Sorry, I've gone out of the area that I've meant to be in, so we'll just quickly analyze that again, back into the design and back to the basic data. And up here I might say, well, actually, you know, I wouldn't want anything less than a 10mm bar, and I wouldn't want to go down to a 75mm spacing, and I can control that. Also control the size of the bar used for punching shear in that sort of fashion as well. So I'll OK to that again and simply auto design all, and again simply quickly flicking through these 4 main categories, I can see that really I don't have any additional reinforcement now being asked for in any of these different zones. Oh, actually I'm not showing the additional, so let's do that to help us. Yes, of course, we're now getting 10s at 300s for the middle zones of these top parts, and the other parts are all happy with the basic amount of reinforcement that I've provided. But really that iterative process, it's entirely up to you how you approach that, how you want to balance your reinforcement of basic versus the amount of additional that you require. Let's have a quick look at the punching shear check that's performed by the program, perhaps before we shift away from this design method. So let's come back to our individual member mode, looking at a member. And obviously, because we're looking at a column now, we're looking at the east-west and north-south steel over the head of the column. But then down here we get the punching shear perimeters that are all checked in accordance with the code. Your 0.75 diameter of column, or dimension of column, punching shear perimeters, and it tells us over here for these perimeters how many bars we require on each of those perimeters at the spacing that we've specified in the basic data and defaults. Now, in terms of printing all of this information out, perhaps one of the most useful tactics is indeed to go and show your additional reinforcement, and those graphics can be printed out in that you know what your basic is provided everywhere, and then you can print a graphic of something like this to say what the additional amount required is. Also, you can print out really just this type of text output, and there's a full print manager for doing that. So you can say in the print manager, well, I want to print my design moments, my east-west, bottom strip steel, and all of those types of things, and this would print this style of output. But then you can also say, then I would like the actual detailed calculations for certain members, and I can say, well, actually for this member and maybe this column or whatever the case might be, I would like the detailed information printed out in that sort of fashion. I suppose I did say that actually I would take a look at the quantities or the values that were of moment that were produced in the analysis and look at how they interpret through to this area. And if we can recall that we had the east-west column strip steel, we had a sagging moment of this value here, and of course the code tells us that in this type of zone you take 55% of this value of moment in the middle strip or in the column strip, and the other 45% outwards into the column strip. So that's taken 55% of that divided by the 2.5 meter column strip width, giving us this value of kilonewton meters per meter force. So it all is very much in accordance with that methodology. So you can see how quickly it is to arrive at values of reinforcement in a slab using this technique, obviously taking into account the restrictions that it does impose on you as well. So I'm going to come away from this method and now take a look at its the alternative technique of finite element analysis. Finite element analysis obviously offers a great deal more flexibility in terms of the geometry. It really removes all of that geometrical restriction from you in terms of your column layouts, or whether you can model things like your balconies or your canopies or shear walls, and all of that type of thing is easily handled using the finite element technique. I should say from the outset that the MasterFrame finite element is not especially a dedicated flat slab design module, but rather a more general finite shell element analytical program. But of course, for the most part, it gets used more often than not for flat slab design, but it is more flexible than that to some extent. Let's get rid of some of these messages here. So I do want to just simply flick through some of the stuff that people have been doing. This would be quite typical of the sort of thing that people would be using the MasterFrame finite element for, i.e. flat slab modeling with shear wall interaction. And we have here a few examples of that, but perhaps showing some more of the flexibility. We have multi-story flat slabs here in finite element with shear cores modeled as finite elements also. More flat slab multi-stories. Quite interestingly, here we have a large structural curtain wall, which is connected via another steel structure to a finite element shear core. So it can be finite concrete elements mixed with steel elements. So you could use this finite element to model, let's say for example, your concrete shear wall and your otherwise steel framed structure to equal benefit as well. So let's take perhaps as a starting point, let's take this little webinar frame that I've created earlier on today. Now it's simulation shape to what we looked at previously, but just highlighting some of the things that can be achieved that are otherwise more difficult in the previous technique. Things like your balconies. We have a few of those here. Things like columns which are offset from the actual slab edges. I suppose that you can classify that as another little balcony. We also have here perhaps a shear wall arrangement which we can model quite easily, and also we have an opening here which goes flat bang in the middle between two columns, so there is no restriction on how many openings you can have, where the openings are, or the shape of the slab, or the layout of the columns, as you would expect from a finite element modeling technique. So let's have a look at how we can, what I have here at the moment is really just a frame, and this frame is put together in the same way that you would put a steel frame together, a concrete frame together. At this stage in time there are no actual differences in them. It doesn't know anything about the fact that this is a slab and these are walls, and we specify that through the setting up of finite element surfaces. So I'm just going to do that very quickly for this area. So in our finite element editor, let's simply go in, and we have a blank surface here waiting for us, and I'll say auto select the surface and window all of that to quickly pick up all the perimeter members to create a flat slab. We have a little opening here, so let's go into the openings, and for opening 1 let me just simply pick in the middle of that to create that. I'm back to my main border, and I can see that that's now been excluded. The different characteristics of this surface are found in the different tabs in the other areas. For example, my material property, I can come in here and specify a material thickness and some basic analytical material properties. It is really most convenient to model the gross concrete isotropic section for the analysis purposes, and that's quite acceptable to do so. So I'm just going to pick up a C30 isotropic material from the little inbuilt library we have here, and applying that we have then obviously all the basic properties. I'm just going to change that thickness to 250, which I think was the slab thickness I used in the previous model also. So looking at then other things we can do is obviously place some loading on this slab. So we have here a list of loads, so I can add a new load. It's defaulted to a full surface area load, which is fine. I'll make it a dead load in the Y direction, and I believe we had a -5. So quite easily that full surface can be loaded in that fashion. I'm going to think a little bit forward here now about how we will produce the patterned loading on this slab in the same way we had patterned loading automatically set up by the previous approach. And one of the things I need to do in order to achieve that is to specify that the load is indeed an alternate load. Now that's not the end of the story, but that's one of the things I do need to do to get this load to alternate itself. And in a moment or two I'll specify how it will alternate and how it will be divided up. So let's add another load, and we'll make it a live load in the Y direction of -5. I think actually I possibly got my loads mixed up here. For the dead load I had said -5. I think we'll had -1 really for the, because bear in mind the material thickness along with the density here will automatically apply the self weight of the slab for you. But I can go forward and add lots of types of loads, for example a point load, a line load, a patch load. Now just quickly adding perhaps a line load, we'll make it a dead line load, yeah, that's fine, and give it a value of -10. Now what a line load asks us for are setting out points, load points, simply load point coordinates. I haven't specified those yet, but I can quickly set those up by saying, well, I would like to create load point coordinates at all existing node points. And that's simply a two-dimensional coordinate system relative to the local surface axis of the slab. And I can label those load points here now. For example, load point 1 is at a coordinate of 0, 0 in relation to the local surface axis of this slab. But I could take any one of those load points, such as load point 42, for example, and let's just go down to load point 42 and make its y coordinate also 6, and you can see that's offset that a little bit from that. So there is no insistence that a load point would be coincident with a node. In fact, I can add any additional load point I like at any location on the slab. So really line loads and point loads and patch loads can be placed anywhere on a slab using that system of location. So let's go in then and pick some of these load points to say that that goes from 47 down to 42 over to 4, and apply that and OK, and I have my line load in that fashion, which can also be varied by saying comma minus not 150 but 15, so I get a varying load going from one place to the next. Patch loads as well can be added in a very, very similar way. Simply add new patch load and then specify the perimeter of the patch load. But to save ourselves time, we'll not go down any further on this route. Perhaps where I would proceed on this frame is then to create shear walls out of these three locations here. But again, what I'm going to do to avoid repetitive work that we've already gone through, I'm going to pick up another frame here, which hopefully has these things already specified. So when I look at 3D, I can see I've got shear walls, which is really just more finite element surfaces with the borders specified in precisely the same way it was for the slab. There really is no differentiation on how one would do that for a wall as opposed to a slab. And we can very, very quickly have a look at that in this area, second, third and fourth surface. What these surfaces do have is in the edge support, they're saying that I've got a X, Y and Z direction edge support on the bottom member of this slab or this wall, so that it does have a continuous edge support in that way. You might argue that it should be perhaps fixed in all directions as opposed to pinned, but that's easily achievable. So let's perhaps look at how we can analyze this now and have a look at the results. When it comes to finite element analysis, one of the things that we do have to be incredibly conscious of is the accuracy of the analysis, and the accuracy of that analysis is very much linked to the nature of the finite element mesh that we have. Meshing is something that we can very largely control by saying what the default mesh size is, but then we can also control what the mesh is in more localized parts. But I'm going to initially just go through an exercise of analyzing this frame. I think it's already been, no, it's not got its mesh, so I can just regenerate the mesh. So it's got a basic coarse looking mesh, and I can analyze that. Oh, actually we've got a problem with regard to the loading cases. The loading cases haven't been set up properly on this here as yet. I'm just going to ignore that for a second and go into the output, and really what I'm getting at with regard to this, the nature of this mesh is it appropriate? Is it accurate enough to capture the intensities of force and such that I have in different parts of my frame? And one of the ways in which you can investigate that, as opposed to really this being a black box and not knowing where you are with regard to your accuracy, is by examining the maximum percentage error. And immediately I can see here, perhaps turning on the key diagram, that I've got an overall error of 18%, but I've got actually quite a high error of 13 odd percent in some of the locations, which I'm not happy to accept. So quite clearly you can see high errors occurring around the heads of all the columns, where indeed I get stress concentrations. I mean, looking at the values of moment, perhaps pulling it up to 3D to show that a little bit better, increasing the scale, you can certainly see stress concentrations around the heads of these columns, and that is typically where we would need a more refined, smaller mesh to capture that type of behavior. So it's always good to look at that error as the very first thing that you do in your first cycle of analysis. Opening up another frame, frame 4 perhaps, yeah. Opening up frame 4, I can see that I have here a more refined mesh around the heads of lots of these columns. And quite simply all that's happened, and this is something that one would do really the very first time you set up the slab, you don't really need to know that you need to do that. By looking at errors, it's always a given that one would refine the mesh around the heads of columns. In the meshing we've got these local mesh intensities, and in this example we simply have picked up all of the nodes. Might be quite difficult to see some of those nodes there with the scale that they're drawing at. There we go. The red nodes are specified to have a smaller 0.15 meter mesh size at a certain radius of influence, causing a more refined mesh and hence a more accurate analysis around those locations. Now coming back to the alternate loading that I specified earlier, if you remember the loads were DAs and LAs, etc. We have here an alternate load area specification whereby I've simply picked up the panels in this region to say that they are belonging to load set 1. These belong to load set 2, these belong to load set 3, and these belong to load set 4. That's something I've had to set up and specify, so you have ultimate flexibility in the finite element analysis to how your loading is patterned. Now those patterns, for example, it is important to note that load sets 1 and 2 form a pair that will pattern load in one direction. Load sets 3 and 4 form a pair which will pattern the loads in another direction, in a very similar way to the previous traditional flat slab design program. And how the actual loading cases then are set up to go along with that are, first of all, I've got load sets 1 and 2 together, which is really the whole slab loaded with fully factored load. And then I've got sets 1 and 2 with a pattern in each direction, load sets 3 and 4 with a pattern in each direction, and it's as simple as that, producing strips that are fully loaded and unfactored dead only and such in the two directions in two different permutations. So let's analyze that what we have here. And let's have a look at the output. So in the output this time, with regard to maximum percentage error, you can see, albeit my overall percentage error still looks to be around the 12% mark. I'll just take that font size down a little bit as well. And but I certainly get a much reduced error in some locations. Now the peak error probably has increased, but I'm not overly concerned about that because that is understandable to some extent, because the more refined the mesh, the more the point of what we call singularity increases in intensity. We're not actually that interested in what the results are at the very, very peak of this column over the head of the column, because we can ignore those values, or we can peak smooth them, as we call it, to try and look around the column at the face of the column as opposed to what's going on at this point of singularity, which is prone to error and not really what we're interested in anyway. So let's have a look at these values of moment, and for example we can look at all sorts of different quantities. Perhaps it might be interesting to look at the mx, which is the value of moment going in this direction, or if you like, bending about this axis, but going in that direction, and looking at it as a 3D type of image. Sorry, I'm moving from one quantity to the other instead of changing the scale there. And I have something automatically turned here on called peak smoothing, and you can see the actual extent of some of these peaks and the severity of them, which is indeed quite correct, because the column was modeled as a pin ahead of infinitely small area. It has its axial stiffness and its bending stiffness interaction, but the actual area of the column with regard to the slab is an infinitely small pinpoint. And what do you get around pinpoints? Massive shears, and hence infinitely high bending moments, which cause these points of singularity, but they're not real, and we can employ peak smoothing to take them and turn them back into much more sensible values. So for example, a peak smooth value of 196 without the peak smoothing gives us a value of 349. So that's certainly the more sensible value that one would use to design to. Let's take off this here. I've turned on the value to show the characteristic points here, which is quite useful as well. This is indeed for one loading case. I can look at the different, say for the alternate cases, and well, this is actually more relevant for the MX moment, but the alternate case in one direction and the alternate case in the other direction, in that east-west direction of loading which is pertinent to the MX value of moment. But let's have a look at these values and how we can then use them to give us design answers, areas of reinforcement, and how far we can take this. The design is actually all done in this area, in this interface. Now, I did say earlier this is not a design program as such, but we do give you facility to look at areas of reinforcement which come directly from the values of moment. In fact, the value of moment that we work with for the area of reinforcement is the wood armour moment, as you would expect, which takes the basic MX and combines it in a fashion with the twisting moment to give you an overall equivalent design moment to work with. So the value MRX of moment then gets used to produce the area of steel required, and we break that down into the top and the bottom for each of the two directions. So if we, for example, look at the bottom XX value of reinforcement, so this is the reinforcement going in this direction. One can see from here, and I've already slotted in a few values here. Let me just come back to that bottom XX again, sorry. That I've put in a limiting value of 700 on, so I'm if you like, filtering out some of the spuriously high values that occur at unrealistic locations. But basically we can see here values of reinforcement that are required in this region. One would ultimately need to be looking at the ultimate envelope to see the overall values, and you will see those values increasing, certainly obviously in the sagging regions because of the patterned loading effects. But also in here I've also said I want to minimize the number of contours I get and specify my own contour values such that I get a delineation at points that make sense to me. For example, between this location, which is 0, and this location, which is the 225, well actually sorry, this location which is 0 and this location which is the 225, I know that a 225 mesh will suffice. Now, I'm not saying that you provide your reinforcement in that fashion, but that gives you an indication of how the contour can be split up to give you appropriate sort of areas of reinforcement at breakpoints which make sense to you. All of this information can also be exported to a DXF file using the when you say you've got contour lines only, i.e. just displaying the contour lines without color shading, that can be exported to the DXF file, which you can overlay onto your actual detailing drawing, and hence then are able to provide areas or detail the reinforcement to these lines of delineation of areas of reinforcement. But obviously you guys that are sensible engineers will interpret these results in a more rational sense to provide rational representations of reinforcement. The contour representation of reinforcement does get a lot more difficult when we come to look at top reinforcement. So the top reinforcement in the XX direction, we look at it here and we see that, let me just go to just the ultimate loading case here, that we do get indeed quite high values, almost 3000 millimeters squared per meter of reinforcement up at this maximum point. That might be quite difficult to see, but that is what we're looking at up here. Now, the problem with looking at reinforcement in the top in a contour fashion is this is a value at a distinct point in the slab. If we look at that value in 3D, well, it's quite skewed when we look at it in 3D, but really that's telling us that, and as we saw when we looked at the moment as well, that we get a very peak value of moment here which dissipates quite rapidly to the surrounding regions. So to design for the peak value is very onerous on ourselves, and this is where section diagrams, particularly with strip averaging, play a big part in making that representation of reinforcement much more sensible and rational to examine. What I have here already set it up is, well, I have a set of section diagrams here which are all grouped under one set called AS required top XX, middle half of the column strip. And if I look at one of these, if I just say not to show all but just to deal with one particular one, let me just change the scale here so I can look at certain values. And sorry, I've changed my quantity there where that's not what I wanted to do. I want to go for AS required top XX and bring that scale down again. And what I'm looking at here, without the peak smoothing or without the strip averaging, which I'll talk about in just a second, again I'm getting quite high values, which is exactly the same value that I've got in the contour. But the benefit is that I can say, well, let's strip average it. I average it over a design strip width of 1.25 meters. Now the reason why I chose that 1.25 meters here is because I'm thinking about dividing this up in a similar way to the 8110 approach in terms of its way in which it looks at column strips and the size of column strips, and also the way in which it says a column strip has a middle half and two outer quarters. So it's entirely up to the engineer as to how he lays out these strips and the sort of size of strip averaging that he employs, but it does make sense to me to employ the similar sort of approach as the flat slab design technique of the 8110. So this does reduce that value from around, I think it was 2,300 to a much more sensible value. And if I show all of those strips together, which are all individually shown in this list, I can see that certainly for this region up here, whereby I think we had almost a 3,000 value of reinforcement, that reduces quite significantly to a more sensible value. Now I have here another set for the top in the YY, which I might complete by saying that I want to add a new one, and I've got a strip that goes from that point to that point with averaging of 1.5 as the spacing is a bit larger in this direction. So that would be your equivalent half of the strip, and showing values to give me values, and I could add new and add another one in that fashion. I have another set here of just a few little strips that represent perhaps the outer quarters of this overall, which would be 2.5 meter wide overall column strip. You've got a 1.25 middle half and two 0.625 meter wide outer quarters. Again, all in a method that following the method of the 8110, and I am getting quantities of reinforcement there for those. I can also investigate my punching shear, not reinforcement. We don't design punching shear reinforcement in this method because we haven't actually specified any or what our area of reinforcement provided is, but we are able to look at, instead of line section diagrams, we can produce rectangular section diagrams, and again not showing all but just showing perhaps one. I can see for the section diagram what the values of shear are around a certain columns perimeter around that column head. Now many people say, well, we wouldn't really need to do that, we just take the value of the axial force in the column and divide that up over strips in the way that we would do it with the 8110, and that's absolutely fine. Obviously where that does let you down a little bit is where you've got unequal spans and things like openings, which do vary the shear from one side of the slab to the other, and you can use those values of shear obviously to do your manual design for your punching shear steel that you may require. That is indeed the extent of what I'm going to look at today, so we've completely run out of time on the two different design approaches between flat slab design using the traditional 8110 techniques, and also then on the other hand the MasterFrame finite element approach. I would like to remind you also that this video will be is being recorded and will be produced and uploaded to our website in the normal fashion, and in fact on the front screen of the Masterseries in a few days time this will turn from closed to view video like all of these things. But of course you can also view the Masterseries website, go to the user login area, through to the training videos, and in the webinars and pick up the video at a later stage from there also. Just remains for me to say thank you very much, ladies and gentlemen, for your time and attendance here today. I hope you learned something, and we hope to see you at our next webinar. Thank you very much, and goodbye.